Okay. Okay. So last time I was a little hurried because it was Monday. And yeah, I was in a hurry because I had that other test to administer. And so we sort of tried to do a problem in the homework. I think we did part of it turned out okay. But the other part I didn't quite see how to do, and the time was flying by. So I said I'd come back to it. Some of it is this stuff here, actually. And then I looked at it more recently, and I realized it would be hard for you to do with what I've given you in class. So here's the story. We've been assuming stuff. Okay. What have we been assuming? Let me see if some of it's here. Yeah, this is part of it. Equation, so I hope you all can see this. Equation 68 in the book says that a birth-death chain is recurrent if and only if this is true. And I think I just said, let's go with that. And then I explained how to do the examples with it. There was also an equation 60. I'm trying to see that probably precedes this somewhere, which had to do with if you started at a state X and you wanted to get to state A before you hit B for the first time, it had an expression involving gammas for that. And that was equation 60. So I guess what I'm trying to say is there are two equations from the book that we've been using, equations 60 and 68. But we really haven't seen the proof of either one of them. And the proof of the second one, 68, is what's needed to do the problem that was asked about after class on Monday. So I think today is going to be a killer day in terms of math, because we're going to, instead of just giving some relations and showing how to use them. So far, I think we went about as far as we can go with just taking these equations for granted and using them. Some of the other problems in the book are more proof-like. And so in order to do that, you really need to understand the proofs of the equations we've been dealing with. So hold on, maybe fasten your seatbelts. Today looks like a proof day. Now, the good thing is everything's in the book. And so if you've been trying to read this on your own or trying to understand some of the proofs on your own, this will be a good day to see how your understanding is. On the other hand, if you've just been taking all these equations, equation 60 and 68 for granted, then today is an effort to explain where they came from. Okay. Questions before we get started? So I will be following the book pretty closely. So let me tell you what pages we're looking at. It's the same pages that we've been doing, but now we're going over it in more detail. So it's section 1.7, which starts on page 29 and goes from there. So equation 60, which is goal number 1, or as far as that goes, equation 59 and 60 are about the same. They're on page 31. So that's one objective. Objective is to explain how the authors got 59 and 60. The second objective would be how they got this result, which we called, let's see, I think it was 68, but I'm looking just to make sure. Yeah, 68 on page 33. Okay, so that's what we're doing, skipping over the examples because we've already done the examples. So let's start from the beginning. So let me put the book somewhere, trying to see if this is going to work for me in terms of, I'm trying to figure out if I want to stand up. Maybe not, but if I don't stand up, then I think I need to move this back. And move this down. Got too much stuff on my plate here. All right. So let's just
7.
page here. So add a new page. And put some lines on it, then we're off and running. Okay, so behind everything we're doing is this fundamental diagram. So I'll put it on the board one more time. We have states 0, 1, 2, 3, and in general, but they may go on forever, but this is enough. And we have transitions that go up by 1 and transitions that go down by 1. The ones that go up by 1 are called the P's, and they're indexed by where they're coming from. P0, P1, P2, P3, etc. Diagram continues in this manner. The ones going down are called Q's. This is fairly standard. Most books adopt this notation. And then you could have some return probabilities. So this would be R1, 3, and so on. And over here, since you can't go down, your 0 is sort of your boundary here. You would just have a probability of 1 minus P0. And the functional assumption of any of these would be that if you're at state X, if you take the return probability, add it to the probability of going up, and add it to the probability of going down, that would give you 1. And that's going to be the case whenever X is at least 1 onward. If this is an infinite chain, we might as well think of it that way, then the state space is 0, 1, 2, and keeps going forever in this manner. So that's what we're looking at. That's a birth-death chain. Okay, so what's the objective? The first objective is to try to find a formula for this. So the book lets u of X be the following. If you start at state X, you want to know that the time you first hit state A is less than the time you first hit state B. So these are the first hitting times, which we've talked about. And the assumption, at least at the start here, is that X is the
Check my email here. Cool.
between A and B. Okay. So this is what we're trying to find a formula for. And by the way, I I've mentioned the history a little bit. This is sometimes called excuse me, the gambler's ruin problem. And so it goes back to the mid 1600s, and it's been refined since then. So of course, what you're seeing today is not the arguments exactly that they gave back then, but it has a lot of what they did. Okay, we assume some initial conditions. So the initial conditions are the following. Initial conditions. So here we're picturing the states sort of linearly related, where X is in the middle, A is less than X, and B is bigger than X. And so we're picturing this to mean we started at this intermediate state and want to know the probability that the time we first hit A is less than the time it takes to first hit B. So that's what we're trying to figure out. And so for initial conditions, we'll say that if you somehow started, so suppose you started at A. Well, if you started at A, that would mean that X is A, and that's not really the case that we're really interested in. But if you actually presume that you actually started at where you want to first hit first, then the time to do that, the probability to do that would be 1. In other words, if you start, you want to either first hit this state or this one. If you start at this one, then you've already hit it. And so that would mean the probability that this time is less than this time would be sure, because you don't have to go anywhere to hit it. You're already there. So that's sort of an initial condition. And similarly, let me see if I got that right. Yes. What would be UB? If you actually start at state B, which is what this is saying, because we're putting in for the initial position B now, well, if you start at B, the probability that you would first hit A before getting to B would, in a sense, essentially be vacuous, because you've already hit B, because you've already started there. So this is going to be taken to be 0. And you can think of it just in summary. If you've already started at A, the chance of hitting A first is certain. And if you've already started at B, the chance of hitting A first is impossible, because you've already started at B. So you hit that first. Okay, so these are initial conditions that we'll impose. Let's put a little box around it so we keep those in mind. Those will be useful the rest of the way. Okay, and the first step in what he does the following. He essentially assumes, so he says, consider Y to be a state between A and B. Now you may say, why does he pick Y to be a starting place between A and B? Because you've already done it with X. You made the same similar kind of assumption up here. It turns out he's going to sum over this index later. So he doesn't want to call this X. He wants to think of this X as a definite place. And he wants to think of this as any place in between. Okay. And so how does the diagram look there? Well, Y would be a state in that picture. And you can go up to where? State Y plus 1. I'm just putting in the diagram. And you go down to state Y minus 1. The chance of going up would be PY. The chance of going down would be QY. And the chance of returning would be RY. Okay, so, and what he says is we can write a recurrence relation in terms of this stuff. So suppose you start at y. If you started at y, what happens one step later? Well, there's three possibilities. If you start at y, you either go down, or you remain where you started, or you go up. Okay. So, so you can think of it as a tree, if you like. Starting at y, you have a path going this way, literally going this way or this way. So suppose you go down, which would have probability qy. Then you're at this point, and you still want to get to A at a time that's less than the time it takes to get to B. And the probability of doing that, if you're here, would be u y minus 1. So we're thinking of this sort of as a two-step event. The first step is from y, you either go down, remain at y, or go up. And then the second event, no matter where you go after one step, you still want to get to A in a time that's shorter or less than the time it takes to get to B. But to do that, the probability of doing that, given that you started at y minus 1, is this by definition. And then there's an or. You could have looped. And then you would be getting, be getting to A before getting to B, but you will have, let's see if I got this right. Yeah, but you will have started at the same place that you were starting and just used up a step. So that would be u of y, because you're really starting from the same place. You return to it. What else is possible? You could go down, you could stay here, or you can go up. The probability of going up in one step is p sub y. And then from there, you want to get to A before you get to B. So that would be this thing again. It would be u, but it would be u based upon starting at the state y plus 1. So I think of this essentially as the sum rule. After one step, you're either here, here, or here. The probabilities of being those places are qy, ry, and py respectively. And then from there, you want to get to A before you get to B, which is by definition u of y minus 1 here because you're starting at this point, u of y here because you're starting at this point, and u of y plus 1. You can read that, yeah. U of y plus 1 because you're starting at this point. Okay, this is what's sometimes called a recurrence relation. It tells you how the probability of getting to A before B starting at Y is related to what happens after you look at the first step you can make. Questions about this relation because it's sort of key for what we're doing the rest of the way. I hope it's clear. Okay, so it's got a lot of letters. And by the way, this argument has a lot of letters. So if you're taking this stuff down, or I hope you're either taking it down or at least comparing what's in the book. The argument I'm giving is pretty much in the book, but I'm adding explanations where I think they're maybe a little short. Okay, so the next thing the authors do is they say, well, we know this relationship holds for all states other than 0. And so why don't we use that to get rid of one of the unknowns? So what they do, they use the relationship that r sub y is just 1 minus p sub y minus q sub y. And again, that's you could bring these two probabilities to the other side. And that's simply saying the probabilities emanating from y have to total 1. You either go down, you remain here, or you go up. So the probability of going to one of those 3 places is equal to 1. And if you solve for the return probability, you will get this. Okay. So what do they do next? What they do next is they substitute this into this equation. All right, so when you do that, you get y is equal to qy u of y minus 1 plus ry, but ry is all this stuff, 1 minus py minus qy times uy plus the rest, the substitution's already been done, py times uy plus 1. Okay, so that's just substituting, getting rid of one of the variables or one of the, the r's in terms of p's and q's. Okay, now from here, probably what a nice thing to do would be to expand this out a little bit. So let's do that. So this one will leave alone, u times u of y minus 1. But this, we can multiply u of y times each of these 3 terms. So this times this, we're just distributing, is that, and then minus p sub y, u of y, and then minus what, q sub y, u y. So I've distributed everything there, and then just reproduce the last term as it is. Y times uy plus 1. So that's just the distributive property of multiplication over addition. And now there are some things in this, on the left side, we still have uy. So there are some things that can be canceled here. Let me see where they are. Well, uy on both sides can be canceled. And then the rest we want to group. So group this first term with the third term. And then group the second term with the fourth one. And if we do that grouping, what we would end up with, we already have 0 on the left side. So, and grouping this one with this one, but there's a common factor of qy. And it turns out that what the authors do is they factor out the common factor of minus qy. So this would be minus qy times uy. That's this guy. So this times this is that guy. And then here, since you already have the minus, you need to put the minus in here so that it all works out. Okay, so all you need to check is this times this is this guy, and this times this is this guy. And then do a similar kind of factoring and grouping of the ones that are doubly underlined. So we pull out the py, and what's left would be uy plus u. This one's not written well. That a little better. So that should have been this times u parentheses of y plus 1. Okay. So when I pull out the py, I just have u y plus 1 here. from this one, and this one, we get the minus y. So you can check that the two underlying terms here are the same that you get when you distribute py times this, you get that, py times that, you get this. Okay, so we could now write this in a slightly different way. We could, well, let me just do it and then hopefully we'll see why. So what I want to say, following the author's argument, is that uy plus 1 minus uy could be seen to be equal to qy over py times uy plus 1 minus uy minus 1. Okay, so perhaps a good way to think of that is bring this first term over to the left. Yeah, well, all right. You can, okay, it's not exactly the same, but I'll still describe it. Bring this term to the left and then divide both sides of the equation by py. So on the left, you'd have qy over this difference by py. And on the right, you would just have this difference. So it's just moving things around. And this they call in your book equation 56. Okay. Algebraically intense. Any questions so far? Okay. If you do have a question, if you're lost or didn't see something, it's good to ask. And what's the presumption here? The presumption here is what we said above, but we probably should carry it down. Y is strictly between A and B. So in this equation here, this is really for Y between A and B. Okay. What comes next? What comes next is to rewrite this in the notation that we've already seen. So set gamma y equal to the product of the q's divided by the product of the p's. And it's presumed here that y is what, bigger than 0. Okay. All right, so if you do that, what does this, you can rewrite this equation as follows. So this becomes uy plus 1 minus uy. And instead of writing it like this, you can write this portion as gamma y divided by gamma y plus 1. Oops, gamma y minus 1. And then the rest is still the same. Well, this gamma y is this. And if you looked at gamma y minus 1, it would look like the same product up to what? Qy minus 1. And P1 down to what? Py minus 1. And if you divide this guy by this one, all the Q's will cancel and all the P's will cancel except for the last two, which gets you back to this. So this is just a different way of writing the same ratio. And at this point, it looks more complicated than it is, but you'll see why they do that in a moment. Okay. Now you could well, actually, you'll see it now. So what we do next is to say, look at what's going on here. On the left, we have, oh goodness, that's not going to start. On the left, we have the difference between u, y plus 1, and uy. And over here, we have the difference between uy and uy minus 1. And basically, those differences are just the same, but they're one off, right? This is going from y plus 1 to y, and this is y to y minus 1. And the connection between them is there's a constant that you multiply this one by to get that one. Well, you can repeat this. Let's do it one step more, at least. So I'm just tacking onto this equation here. I'm going to keep the gamma y and the gamma y minus 1 there. But this difference, I'm going to pretend that that's the bigger one. And so I'm going to subtract y from y, I'm going to subtract 1 from these. Well, if I do so, I'll get something that looks like uy minus 1 minus y minus 2. But when I do that, in order to be faithful to what this is, I have to multiply this thing by something that looks like this, and it will look like this, except what? Y will be replaced by gamma of y minus 1, and the same on the bottom. So that will become y of y minus 2. In other words, this is the constant. I multiply this difference to get this portion. So it's the same equation. And if this makes sense, and I hope it does, we keep doing that. We keep replacing this difference so that the difference occurs one step below where it is now. So the next one would be uy minus 2 minus uy minus 3. So if we keep doing that, same kind of substitution, what we're going to get in the end will look like this. Gamma of y minus 1. We just got gamma of y minus 1 times gamma of y minus 2. The next one would be gamma of y minus 2 divided by gamma of y minus 3. And so it would go, and it takes a little while to convince yourself of it, but where this comes to the end is when you get finally down to A. Remember, y was between A and B, and here we're decreasing y, so we're getting closer and closer to this. So the end of the line of this argument occurs when you get down to gamma of A plus 1 divided by gamma of A. And in that case, what's left? In that case, what's left is a difference that looks like u plus 1 minus u of A. This convincing yourself, I don't think it's hard to convince yourself you could apply this identity over and over again where y is decreasing and get more terms that look like these. Maybe it takes a little more thought to see that this is the end of the line. But I'll let you convince yourself that that pattern is indeed what's going on. And now we can simplify this because the gamma of y minus 1 and the gamma of y minus 1, they cancel each other, and gamma of y minus 2 and gamma of y minus 2 cancel each other. And so all of this could be simplified to just give us what? The gamma y up here won't get canceled, but all the other gammas will get canceled except for this guy, because this guy would have been canceled by the gamma of A in the next, but there is no more. So you're left with this times u A plus 1 minus u of A. Okay. So if we just keep, that's the reasoning, but if we just keep the result would say what? It would say u of y plus 1 minus u of y is equal to gamma of y divided by gamma of a times this difference. So that's the result from first that side of this equation all the way down to this one. And this in the book is called equation 58. So for those who are keeping score, we're trying to get to equation 60. And so we're getting closer. And once we get here, what we've assumed throughout was that A was strictly between this and this. But then when they get to 68, they actually say this holds even more generally. It holds for what? A even being allowed to equal B, A. Y even allowed to be equal to A. So we already knew that this argument would hold when A was strictly less than Y, and strictly less than B. But they're saying it even holds, something like that. They're saying it even holds when Y equals A. Well, when Y equals A, this side would become U of A plus 1 minus U of A. And when Y equals A, this just becomes gamma of A over gamma of A, and that is 1. And so you do get equality. So this equation even holds a little more generally than we first thought. Okay. Questions thus far? There's a lot on this page. I have to decide if I want to keep pressing it. Maybe. Because it's easy to scroll back and forth. Okay, any questions on what we've done so far? Now, the obvious question is, do you need to know this as a proof? And I think the answer is going to be no. But some of the techniques, we're going through this because some of the techniques are appearing in the homework. That's one reason. And the other reason is, you're not just here to memorize formulas. It's good to know where they're coming from a little bit. So this is an explanation. Let's go on. Okay, so moving on. Here's where things become a little more interesting even. Most of this has been algebra. Let's go up. I've got a little more room. Okay. This equation, the preceding equation over Y, where Y is going from where Y ranges from A plus 1 to A plus 2, all the way up to B minus 1. Okay, so we know this equation holds for each of these values, including A, as we just pointed out. So let's sum it up over all of these values. So what does that look like? it looks like the sum of this stuff, u of y plus 1 minus u of y, and you're summing from a to b minus 1. And on the right side, you get the same kind of thing. So you have a summation going from a to b minus 1, but of this quantity over here, gamma y over gamma a times u of a plus 1 minus u of a. That's all in the sum. Okay. Maybe the best news or the easiest news is this is a telescoping sequence. So if you wanted to start from the top down, if you put in b minus 1 for a, you get u of b. This b minus 1 plus 1 is just that. U minus u of what? B minus 1. So that's the term you get when you put in the top term in the sum. When you put in the next term down, that would be b minus 2. When you put in b minus 2, this becomes u of b minus 1 minus u of b minus 2. And now you can start to see that this term will cancel this, and that will continue. That kind of cancellation will continue because you can see it right within the summon until you get down to the end. So the very last term here, I'll write it over here, would look like u of a plus 1 minus u of a. And the one preceding that, which occurs when y is a plus 1, would be u of a plus 2 minus u of a plus 1. So, and then there's a whole bunch of terms in between. So on the right side here, it's fairly clear, I hope, that this cancels this, and that this one will cancel the next one over here, and so on until you get down here. This will cancel what's preceding it, and these two, you can see the cancellation. So like the usual telescoping series, you just get contribution from the top, which in this case is UB, and then minus UA. Okay, that's on the left side of this equation. What goes on the right side? Well, on the right side, the sum is over y. So a is a fixed point, and therefore this product can be taken through the summation because it's a constant with regard to the index. So we can factor out the UA plus 1 minus the UA because it's a constant with regard to the sum. Fortunately, over here, I lost what I wanted. What was it? Was it just UB? I think so. Okay. Getting a little fussy here. Let's see if I can write this in a way so I don't lose stuff. So I'm factoring that out, but I could also factor out the gamma of A because that doesn't depend on Y either. That's still on the bottom. And what's left is a sum over gamma y, where y is going from where? From a to b minus 1. Okay. Okay. Questions about that equation? And that recurrence relation that we had up here was done with this in mind. So this has all been worked out whether this is working. Looks like something here I've lost. I hope you have it from above. Any case, we're down to this. We can do some more. What can we do? Well, we recall U of B was 0. So we call U of B was 0. And U of A is 1. These are our initial conditions. Okay, so what is this on the left side? Well, U of B is 0 and U of A is 1, so this is just -1. And if you need to recall, I guess I can scroll up. Hopefully, there they are. The initial conditions. U of A was assigned to be 1 and U of B was assigned to be 0 from the beginning. Okay. So, so on the left side of this equation, we got -1. What about on the right side? Well, let's see. The right side we just keep as it is. So let's just do that. So that's U of A plus 1 minus U of A. All of the gamma of A. And that's times the sum. Y equal A minus 1 and Y. Okay. Now, what we'd like to do basically, all we want to do is keep this constant the way it is. Well, if we multiply through by -1, this becomes 1. And this guy just becomes UA minus UA plus 1, because you're multiplying by -1. And the rest is the same. So, okay. And from here, what they do next is just solve for this portion of it. So UA minus UA plus 1, that difference divided by gamma B is just 1. And divide both sides of the equation by the sum.
Professor?
Yes, go ahead.
How come the gamma A became a gamma B in the denominator?
It was a mistake, so I'm glad you said something. Thank you. This was A, but then this should have been A as well, right?
Yeah.
Thank you. Okay, so we get this fact, and now they say go back to equation 58 and substitute this in. So substitute this in. this into equation 58. Well, hopefully I've got 58 labeled somewhere here. There it is. Oh, but it got damaged. Oh, sad. Okay, but that's, let me see if I can just restore it. 58 said this. It said, before it got damaged, u of y plus 1 minus uy was equal to this. And over here was u of a plus 1 minus ua. Okay, so that wasn't too bad to restore. So if we look and see what we're trying to substitute in here, at some risk, go down and see. I think we just want to substitute in what's on the right here. Let's go back and look at it. UA minus UA plus 1 over gamma A. That's what was on the right over there. So substituting for what's on the right by 1 over the sum is what we want to do. Okay, so what we're going to get, going back to 58, we're going to get this difference is equal 1 over that sum. So another so. So we get u of y plus 1 minus u of y is equal to this. Well, I guess I have to be a little careful. U of A minus this over this is what I'm substituting, but the gamma of y still stays on top. So what we get is gamma y up top, and then we get this on the bottom. Okay. And this holds for y strictly, or not strictly, greater than or equal to a less than b. Okay, so basically we substitute this back into 58 and we get this equation. This is almost what we want. Yes, but there's one more thing to do. And the last thing to do is take this equation and sum this equation, the preceding equation, from where? Sum over y from x plus 1 all the way up to b minus 1. So this thing was another y we had in this range. So we're summing, now what was x? X was something from the beginning that was strictly between a and b. So there's two different indices here. But y is going over here, and we're summing over the x values from x plus 1 to b minus 1. And if you do that, you can see on the left, you're going to get another telescoping series. So let's write it, and then we'll worry about it. So on the left, it's going to look like this sum, u y plus 1 minus uy. And that sum is going from where? Y going from x to b minus 1. So that's what's going on the left of this equation, the sum. Now this one, by is a constant with regard, or gamma y is a constant with regard to this. No, we're summing over y, my bad. This is a constant, okay. So when you sum the right side, this is a little tricky because this sum has already happened. So when you have a sum that's already done, this is a constant down here. So what this becomes is the summation over the variable gamma y, where y is going from where? Y is going from x to b minus 1. Because that's where the y is a variable, but that's all over this constant, which happens to be a sum that looks like this. Okay, now that's tricky. It's tricky in a couple ways. We've already summed once an equation. Now we're summing again over an equation. But the beauty of it, I suppose, is that this is a telescoping series again. Okay. So what does it look like? If you work from the top down, when you put in b minus 1 in here, you get ub. And then you'll get ub minus 1. And if you put in b minus 2, looking from the top index down, you'll get u of b minus 1 minus u of b minus 2, and so on. Where's the end of the line? The end of the line occurs when y equals x. So when you put in x here, you'll get any terms, and then the last one will be u of x plus 1 minus ux. Okay, but again, just as the other telescoping series works, the terms in the middle get canceled with each other. Everything gets canceled except for this term, and this will get canceled when it precedes it, and this one. So the left side of the equation becomes just ub minus ux. And that's, well, on the right side, we're just going to leave it as it is. So it's the summation of gamma y going from x to b minus 1, divided by the summation of the same expression, gamma y going from a to b minus 1. But remember that u of b was 0. If you started at state B, there's no way that you would have the first time to get A to be less than the time it takes to get to B, because you're starting at B. So by our initial conditions, this is 0. Okay, so okay. Making sure I've done this right. You'd be off by minus sign. I'm looking at it. Let's look at what's going on up here. Let's go back to 58 and see if I've messed up. No, I think 58 is fine. I have y plus 1 there. Yeah, I think that's fine. Oh, this may be the mess up. Yeah. I'm looking for a minus sign error. So maybe it occurred up here. So I multiplied both sides by -1. That became this. And so I got this. That's fine. Still looking at the 58 substitution. So I think I'm okay up to here. Yeah, there's my problem. Okay, so this part is fine. But I think where I'm hurting is 58. So let's go back to 58. So I'm going to circle this one so I can keep my eye on it. If we go back to 58, that's this. And the disconnect is this has a UA plus 1 minus UA. And this one has the sign reversed, UA minus 1. So I'm not sure. I think that's where I messed up. So 58 is saying this. So UA minus 1 minus UA over gamma A. This should be minus, right? So this, if I want to make this so I can substitute it in, I need UA minus 1 minus UA over gamma A. And I have the negative of that. Yes. UA plus 1 minus UA over gamma A. I should put in for that. I should put in minus this, right? So okay, what's the easiest way out of this? Easiest way out of it is, this is all true. But what I want to substitute in, I need UA plus 1 minus UA. So I really want this to be plus minus. So I want the negative of both sides of this equation. Apparently. I want to make sure I'm doing that right, but I'm missing a minus, and I think that's where I'm missing it. Because here I have a UA plus 1 minus UA over gamma A. And I can't just substitute this in directly. I'd have to substitute the negative of this in. So if I do that, then this would have had a minus. Let me make sure. Yes, there would have been a minus this thing here. So this should have been minus. So if this becomes minus, then what gives over here? I think what happens, and I'll let you check because time is gone, this should be a plus, and this should be a minus. Okay, so ux is equal to this. And that's 60. This part here is equation 60. Okay, so we spent the whole time trying to get equation 60, but that's the hardest one. Any questions on this? There was a little confusion at the end. I missed the minus sign, but since I think I caught it at the end. It's cool because you're getting this function of x in terms of things you know. Summations of the gammas, and the gammas have p's and q's in them. And the summations are just varying over different things. By the way, this one is what? This is the probability starting at x that the time it takes to hit A is less than the time it takes to hit B. If you wanted the reverse, the easiest way to get the reverse would be to take the complement of this. And what would that be? The complement would be found just taking 1 minus this. So if you want the other formula, the chance, let me just actually see which one is. Okay, so this is not 60, this is 59 in the book. But if you wanted 60, looking at it real quickly. Yeah, if you wanted 60, 60 is the complement where it's the chance of hitting B is less than the chance of hitting A. That could be found just by taking 1 minus this stuff. So you're going from y equals x to b minus 1. And on the bottom, you have the summation. You have a y going from y equal a to b minus 1. And you might say, well, okay, and how do you do that? Well, you can get a common denominator. So the common denominator here would be this. So how this would go, you multiply, you'd have something on top that looks like this. The summation of all the gamma y from y equal a to b minus 1. And then you'd be subtracting off all the gamma y given by this from y equals x to b minus 1. And on the bottom, you would just have the common denominator, which is this guy. But you can simplify this because they're summing the same terms. So this is actually giving you what? it's giving you some of these terms get canceled off from these. And what you're left with are the y's going from what? X plus 1 to b minus 1, gamma y, divided by the sum. And hopefully, I did that wrong, so let's see. I'm going from A to X. I've got to remember where everything is. A is between X and Y. So this one, this is the bigger term. But again, I'm getting plagued a little bit by minus signs. Let me see. This one we got, this is 59. Y equal X, and then we went from this to that. And we just subtract things from 1. Oh, that's what's wrong. This is not right. This is right. Okay. So you're going, this is the bigger term, and you're subtracting this. So it leaves the sum from the earlier terms are what are being left. So it would be going from change this to be A and change this B to be X. Let's make sure maybe it's X plus 1. So this has all the terms because A is the smaller, so this is the bigger sum. And here you're taking everything of those away. So you're actually summing from X plus 1 up to B minus 1. Okay. And still not right. This part should be easy, and it's not, so maybe I'm missing something obvious. It's supposed to be I had it and I made it wrong. All the terms from X to B minus 1 are being taken off. So the ones that remain start at A. They are the earlier ones. And they go up to what? X minus 1. Finally got it. Sorry about that. But you have to look at the difference of these two series. And you have to remember that A is the smaller between X and well, I think actually B in this case, but that part doesn't matter so much. Between A and X, this is the inequality. I think it was B over here, but okay. So your sum, there are more terms here. You're going from A to B minus 1. There are fewer terms here. So you're removing the n terms, which leaves the earlier terms, which go from A to what? X minus 1. This is equation 60, which is not the one we've used so much. We're actually been using 59, which we did already have here. But once you have one, the other is not hard to get. Okay, I'm done. I'm knowing well over. I'll take a 20-minute water break. The rest is relatively easy, so we'll do the rest next time. Where we got, just for your information, we got to 60 and 59. So this was all the material in the book, basically on page 30 up to the page 31. And what we'll do next time is the part on 32. I might even give a preview of that today for those who hang around. I don't have any more problems to do, because to do the problems, you need to understand. Fortunately, you don't need to understand the techniques of this proof to do the problems. You need to understand the techniques of the part we've yet to do on 32. So I don't think I've got anything more for you to do. So take a break as far as the homework goes. But I think we'll come back next time. There'll be some problems over the weekend. Okay, I'll see you in 15 seconds or so. For those that are hanging around. Not an easy proof. The amazing part is I have most of it on this one slide. So let's start the office hours. Does anyone have a question about any part of it? And then I'm sorry at the end I've messed up with a minus sign here and there. But for most of it, I think it was going fairly smoothly. Any questions on the proof? It's tricky. How is it tricky? Let's see if I can highlight some of the trickiness of it. The first part, believe it or not, I don't consider to be very tricky. This relationship, this is the recurrence relationship for you that you need to play with. Getting rid of R seems to make sense because you don't need more variables. And you come up with this relationship, that the function you're looking for is a function u of a difference, uy plus 1 minus uy. If you reduce the argument by 1, these differences are related to these differences by constants. Qy and py are constants. So that's a key observation. So I'd say 56, which is pretty much just algebra, is important. And here we replace the constants by these gamma constants. And that's just so that we can see the cancellation that occurs here. So in theory, you probably could keep this if you wanted to keep it all in terms of P's and Q's. And then you'd have a lot of product of P's and Q's at the end here, right? So this is just more a bookkeeping device to make it easier not to have all the products in the P's and Q's occurring in the equation, because the gammas cancel, and the gammas have the product of the P's and the Q's in there, right? So that's just, I would say, just a indexing technique. That's not such a big deal. You're still coming away with the same conclusion. However, you got a little more. You now have the difference between uy plus 1 and uy not to be just in terms of the previous one, which is what's going on here, but in terms of the initial one that happens at A, and A is at the start of the whole process. So this is sort of big step in that sense. The difference between these two functions is in terms of the difference from A plus 1 and A, and the constant there involves this, which involves the products of P's and Q's. So it's a more complicated constant. Here comes some of the prettiness of it. If you're trying to find out what these things are, this, if you sum, this becomes a telescoping series. And when the dust settles on the telescoping series, you get an expression for UA on the left side. And on the right side, so the good news is on the left side, you get a lot of cancellation. So you get a simple expression for UA. On the right side, you get an expression that involves the sum of these gammas. So that's where the sum of these gammas come into play. Up until now, they weren't there. But that's an effort to take, as results as an effort to try to find what the UYs are. So you've got UA now. So you've got one value, and this is done because A is known, gammas are known in terms of P's and Q's. So you know what UA is now. And if you know what but you also knew that UA was 1 to begin with. So that gives you this sort of key relationship between getting the difference between UA plus 1 and UA. Once you get the difference between UA plus 1 and UA, then you use this to get the general difference. So you're able to get a hold of this particular difference in terms of constants that are known right here. And then the initial conditions play a part in this because that allows you to simplify what's on the left here. U of A was 1. So that gives you a handle on how to get this difference in terms of what's known. And then once you have that, then you back substitute into 58, which is this thing that tells you how to get this anywhere. And so you back substitute the one you know on the right. So now what's on the right is known, and this is not. And then you do the trick again. You sum over all the y's, and the thing on the left becomes essentially what you want, just ux. So now you've got it for x, and x in this case could be anything between A and B essentially. And then the rest of it is done. So it makes use of a telescoping series technique 2 times. One time to get this guy, UA plus 1 minus UA. And that happens in terms right here. So you can solve for this thing. So that's key. And then making use of this argument here, if you know the difference between the u's between A and plus 1 and A, that gives you the difference between the u's at any y, according to what we did here. And then the cool thing is then you do another telescoping series of this, and it gives you ux in general. So it's very, very nice, very clever. And if someone were to ask me, how does anyone think of this? It's long, but you can see the pieces, right? So the techniques here are something that you like the techniques. These occur in what are called recurrence relations. So the techniques here may be entirely new to some of you, but recurrence relations have to do with things that have differences, and that's a little bit like differential equations, by the way. So some of the techniques are similar to solving systems of or differential equations. Questions? Questions about anything in this proof? Okay, any request? I could go on and talk about the thing I'm going to talk about next time to give you a sort of a heads up on it. We can look at some of the homework problems again. The one that we sort of did last time, halfway, we're not in much of a better, we're in a better place to do it, but we still don't have quite what we need. That was problem what? 26. But we could do 27, which makes use of 26. So we could do that if someone was interested, and then just do 26 later after we see what we need. 28 and 29. I'm not sure whether we can do them, but we might. So I'll take requests on any of those. The only one that I'm skipping for the month now is skip 26B, because that we need to understand the book a little more. So let's skip this one. But I think we could do 27 using 26. And I think we can do 28 if people have questions at either of these.
Yeah, can we see 27?
Say it again, please.
Sorry, can we see 27?
Let's try 27, assuming we can use 26B. Okay, so what is 27? I'm going to turn page because there's too much on this page. I got lucky to use to do. Not get hurt on that page. All right, so now let's look at 27. So 27 says, consider a gambler's ruin on the infinite state space. Show that if, so part A, show that if Q is greater than or equal to P, then rho x to 0 is equal to 1. For all x greater than or equal to 1. Now, in a way, we already did this problem, but we didn't do it the way they're talking about it. So let me at least tell you why we've already done this problem. So it was a couple days back now. We looked at when these were all p's. And when these were all q's. And they were constants. And I think we had a constant r as well. So I think we did this in class. And then these things continue going up and down, p's and q's. Okay, doesn't like me doing that. Let's see if I can share. Okay. Let's see if I can share. Okay, so I don't feel I'm more careful here. Anyway, these things, P is going up, Q is going down, and so forth. Oh, boy. Okay. All right. Let me see. What we did in class before was we used criteria 68, which said we looked at the summation of something that looked like Q1 through QX. P1 through PX. And we looked at that summation. This is equation 68 if you're trying to recognize it. When x going from 1 to infinity. If this is infinite, then the birth-death chain is what?
Professor,
Right?
I don't think you're sharing your screen. If
Well, thank you. Let me see if we share. I thought I had people on board, but no. Now better?
yes,
Okay, so this is all I've written from last time. If this series is infinite, then the chain is recurrent. And we showed that if Q was bigger than P, this on top would have been Q to the X, and this would have been P to the X, and this would have been a geometric series where each term is bigger than 1, so it was infinite. Therefore, it was recurrent. And if it's recurrent, that means every state leads to, has, first of all, every state communicates with each other. And the chance of going from X to 0, wherever X might be, is, since X is recurrent and 0 is recurrent, that would mean these are both 1. So we already did this problem by something in class, namely equation 68. But we haven't proved 68 yet. That's what we're going to do next time. So the question becomes, how do you prove this without using 68? But at least I'm telling you that we already know the result using 68. And by the way, the other result was when P was bigger than Q, then there was a chance that, as I said before, the current is going up. So then everything is transient. But this part of the problem here is looking at it when it's recurrent. Okay, so, and P being Q is, they have a different result. Okay, so how do we get the results of 27 from 26? So without using 68 here. So they tell you for 26b tells you what row is. So 26b says what? Says, oh, I can't use this. I'm having trouble. Let me try to close it and let's actually close. Let me just go to a different screen and see if it's going to let me do it better, because this screen is not working. Sorry for the problems here. So again, I'm going to OneNote. Oh, yeah, it doesn't even, it's telling me I'm having a problem. I know I have a problem. Let me go to a new screen, hoping that works. Sometimes that does, sometimes it doesn't. Okay, so now I have a new screen. Let me share it with you. Okay. It's pretty sad in a way because we did the whole lecture on one slide and now I can't do one problem on one slide. Okay. So from 26b says rho of x0 is the sum from y equals x to infinity of gamma y all over the sum from y equals 0 to infinity of gamma y. Okay, so that's what 26b says. What do the gammas look like? The gammas have Q1 up to Qy, P1 up to Py, and that's for y bigger than 0, and if y equals 0, then what? Gamma of 0 is 1. Okay, so that's what we know about those. And in problem 27, we've got all the Q's being the same and all the P's being the same. So these look like what? Q to the y, P to the y. Okay. So in the case that Q is bigger than P, what is all this going to turn into? Oh, let's see. So it looks like the summation from y equals x to infinity. Gamma y looks like this. So that's q to the y, p to the y. And on the bottom it's similar. Here you go from 0 to infinity. Okay. The difficulty is now what? We're assuming that Q is greater than or equal to Y. Q is greater than or equal to P, rather, sorry. So these are geometric series, but they're what? They're diverging geometric series. So what does it look like? It looks like infinity over infinity. So the question becomes, how do we get 1 out of this? Which is what we're trying to show. I think we can get that in the following manner. So it's almost the stuff we were doing at the very end today, almost. Why don't we do, so this one I'm not positive about. Why don't we do the one, why don't we do B? If we do B, then everything is convergent. So let's do that first. So instead of doing 27A and doing,
Professor,
yeah,
what if we write out the sum? Sorry, I'm just trying to think out 27A, because when we write out the sums, I think we get like that the top is similar to the bottom, except that the bottom it starts at 0, like when we plug in y's,
right.
but the numerator starts at 1. So like, could it be canceled out?
Well, let's go further. Okay, since I have no problem trying it. The other one will be obvious, but let's try 27A since you bring it up. So we could write it as P over Q to the X, right? Plus P over Q to the X plus 1. So the top would look like that.
But we know that X starts at 1, or no?
No, we know it starts at X when Y equals X, right?
Oh, okay. Oh, because I was thinking, because they it says that X for X greater than equal to 1, so I thought we could just start at like 1.
Well, you could do X equal 1. That would be a special case. And
Oh,
I'm doing them all at once just to show you what's happening. The one on the bottom would look like what? P over Q to the 0 plus what? P over Q to the first. And so what you said is true. The one on the bottom has all the terms of that on top and some initial ones, right? And but in this case, P over Q, let me see. Oh, no, okay, actually, this is the easy case, my bad. Because P over Q, what are we assuming? We're assuming for part A that Q is greater than or equal to P. Oh, let's see. No, something's wrong. So these should be Q over P, right?
oh yeah, it's Q over P.
Yeah, so rather than trying to correct it all, I'll just write it again. It should be Q over P to the X plus Q over P to the X plus 1. Dot, dot, dot. That would be what's on top. And then on the bottom, it would be P over X, or Q over P to the 0. Q over P to the 1. Okay, and since Q is greater than or equal to P, what does that say? Q over P is greater than or equal to 1. So this goes along with what I was saying up here. This is a divergent geometric series, so this is infinity. This is also infinity. And what we're trying to show is, in this case, infinity divided by infinity is equal to 1. is there an easy way to do that? You can't use the summation formula because it doesn't converge. Maybe you can do something nice. Let me think about it a little further. So that's what it comes down to. It comes down to having two divergent geometric series. They're both going off to infinity. And you want to say that the ratio is going to 1. Maybe the easiest thing to try to do is to show that 1 minus this quantity is going to 0. So why don't we see if we can do that? I mean, infinity over infinity, typically what you would do with that would be a L'Hopital kind of thing and start taking derivatives, but you're not going to it's not going to get better because they're infinite series and you're still just going to get more infinite series from them. So can we show that 1 minus this is going to 0? If 1 minus, that would be the complement. So can we show, let's call this something, call this t. Can we show that 1 minus t is getting close to 0? So, okay, when you put it in this frame, this becomes what? Basically an analysis or calculus problem. I'm not sure I'm using everything I've got from the previous problem, so let me double check. Yeah, they're telling us this is rho. So what does that tell us? That tells us that this ratio is between 0 and 1 because it's a probability. If we're using 26b. Okay, so this is a probability. Does that make it easier? Not in an obvious way. How about let's try this idea still since we're here. What would 1 minus this look like? 1 minus t would look like 1 minus this quantity. And q over p to the x here, etc. And q over p to the 0th power, so forth. If you took that difference, you could do the common denominator, which would just be this. So what would you have upstairs? That might work. Let's keep at it. So the common denominator would be what's on the bottom, q over p to the 0, plus q over p to the 1st, all the way out. And then this would be this same series. Q over P to the 0, Q over P to the first, minus this one. So in that case, what will you get? You'll get the finite series on top, right? Because these terms all cancel the later terms here. So what you would get would be something that looks like Q over P to the 0 up top, Q over P to the first, up until what? Q over P to the x minus first. And then all the other terms will cancel because you're taking the difference. So you would have this over this. And this would be an infinite series. Okay. Now, at this point, we're done because the bottom is going to infinity, but the top so x is fixed. The top is just a constant, right? So for any fixed x, this series is going off to infinity. This series is getting large, but for P and Q fixed, this is some constant. So this would be considered to be 0. So if that's 0, 1 minus T is 0, and T is equal to 1. I don't know if I like that reasoning so much, but I think it works. Let me see. So we're trying to see what this ratio looks like. That's from 26b. 26b says we can do this. But that's not going to work because 26b has the presumption that these things actually what? Converge. So we can't use 26b to do 26a. So what can we use? Can we use 26a to do 27a? Let's see. If the sum of the gammas goes to infinity, then rho x0 equals 1. Yes. So it's even easier. Forget all of this. Use, so to do 27, to do 27a, use 26a. 26a says that if the sum of the gammas go off to infinity, which they will, because this is a divergent geometric series, then it just tells you that rho x0 is equal to 1 for x greater than or equal to 1. And that's exactly what you're trying to see in 27a. So we're making it much harder than it had to be. If we're going to use 26, if we're going to use 26, we have to believe the results there. So the results of 26a says that if the sum of the gammas diverge, go to infinity, which they do in this case when q is bigger than p, because you have a divergent geometric series that goes to infinity, then the rows are just equal to 1. And so that follows directly from 26a. Does that make sense? So we don't, this kind of argument, this argument is sort of okay, but it's not because we're using 26 B and 26B doesn't apply. Because in 27A, we've got a divergent geometric series. So we have to, I think we were trying to prove too much. Proof is already taking place in 26. So we still have to go back to 26. So what I'm saying is 26A directly leads to 27A. It says the same thing. And what about 27B? 27B should be a direct consequence of 26B, because if P is bigger than Q, then the Q over P series will be a convergent geometric series, which is what B is about. And then you just have the ratio of two geometric series. And so we should be able to use 26B directly. Let's do part B. So what does it say? 26B says that rho of x0 is the sum. Well, let me just write it because it's easier to do the sum. It's the sum of Q over P starting at X, going on Q over P, X plus 1, etc. And on the bottom, what does it look like? Just like what we had before. And this is all rho of X. It's Q over P to the 0, Q over P to the first, dot, dot, dot. Okay. But, so this is by 26B, where we're using that the Q's are all constant and the P's are all constant. What is this? And we're also using that what? P is bigger than Q. So these are both convergent. Not only are they convergent, they're convergent geometric, so we know what they converge to. So let's do the bottom one first. The sum of a geometric series, the 1 plus r squared, something like that, converges to 1 over 1 minus r. So the bottom here would just be 1 over 1 minus r. What is r? What we're multiplying by to get to the next term. So that's this. You can change this if you'd like into P minus Q over P. And if you want, you can now write that as P over P minus Q. So the sum of the series on the denominator here would be P over P minus Q. What about the numerator? The bottom here, if I do this correctly, I think I did, is just P over P minus Q. Oops. It's just P over P minus Q. What about what's upstairs? What's upstairs looks almost the same. In fact, you could just factor out a QP to the X and make it look the same. And then it looks like 1 plus QP plus QP squared, etc. Okay, and so what does this converge to? We already saw what this converges to. This converges to this again, P over P minus Q. And then all you have to do is multiply that by Q X. So the numerator converges to this, and the denominator converges to this. And if you take the ratio, the P over P minus Q cancel, and you just get Q over P to the X, which is the result of 27B. So 27 does follow in a fairly direct way from 26. Should I go over that again, or does that make sense?
That makes sense.
Yeah. So we still have to wait on 26. So here's a question. We still have a little time. Should I do 28? I think I should wait on 26 because the techniques still haven't, the techniques are following on page 31. Whatever. What about 28? Let's see if that can be done. Consider an irreducible birth-death chain on the non-negative integers. Show that if Q of X, P of X is less than or equal to Q of X, then the chain is recurrent. So that's more general. It's allowing the P's and Q's not to be constant, but it's insisting that what? It's insisting that the Q's are the larger of the two. I think that comes quickly too. So for 28, we have a birth-death chain, and we're assuming what? We're assuming that Px is less than or equal to Qx for all x. All x greater than or equal to 1. Fine. Okay. So we're trying to show that it's recurrent. So that will be case A. Actually, this doesn't even follow from 26. It follows from 60. So we know something is recurrent. A birth-death chain is recurrent if the summation of what was 60? 60 said, or 68 rather. 68 said the sum of the gammas gamma x's from 1 to infinity has to be infinite. That's 68. But what do these things look like? What do the gammas look like? Gamma x looks like Q1, Q2, all the way up to QX, P1, P2, all the way up to PX. But if you know that each of the Q's are bigger than the P's, so that means this fraction is greater than or equal to 1, so is this one. Each of them are greater than or equal to 1. So when you multiply fractions that are each greater than or equal to 1, you're going to get something that is greater than or equal to 1. So by the assumptions in this problem, Qx are greater than or equal to Px from 1 on. So that means the Q's are greater than or equal to 1. And now if you're adding up something that starts at 1, I guess. So gamma 1, gamma 2, gamma 3, etc. But these are all greater than or equal to 1. So we do a simple comparison, replacing these by this. And this adds up to infinity. That means this adds up to infinity. That means what? The chain is recurrent. So this follows directly by 68, which we haven't proved yet, but at least we can use it. So this one is just asking you to apply 68. Problem 26 is asking you to do something like the proof. That's why we have color 26, but we'll get back to it. Okay, so let me recap this because it came fast. A birth-death chain is recurrent if this sum is infinite or diverges. If you're assuming the Q's are bigger than the P's, That's the same as assuming that each of these fractions that occur in the gamma are greater than equal to 1. If you multiply two fractions that are greater than equal to 1, you get another fraction greater than equal to 1, and that continues throughout here. Another way of saying it is the numerator is greater than or equal to the product of the product of the q's is greater than or equal to the product of the p's. So that means each of these terms is greater than or equal to 1, which means it diverges. And this is bigger, so that by comparison test, this thing diverges, and therefore the chain is recurrent. Okay, are we starting to feel a little better? 27 is a direct consequence of 26. 28 is a direct consequence of 68. Should we quit while we're ahead, or should we push it? What else did I assign? 29? Twenty 29 is similar to 28. That's we're using 68 everywhere. So what do we know? In 29, we know that qx over px is greater than or equal to what? X all over x plus 1 squared. That's what we know. And if we're trying to show that the chain is recurrent or transient, it all boils down to whether the sum of the gammas is infinity or the sum of the gammas is finite. So, okay, what do the gammas look like? Just like what we have above. So the gamma x's look like Q1, Q2, all the way to where? QX, all over P1, P2, all the way to where? PX. But we have an estimate for these ratios. So what do we know? We know that P1 over Q1 is greater than or equal to what? 1 over 2 squared? Why? Just using this with x equal 1. And then P2 over Q2 is greater than or equal to what? 2 over 3 squared? And similarly, so if I multiply, why am I doing it that way? I shouldn't be doing it that way. I should have them reverse. Q1 over P1. Q1 over P1. This is greater than or equal to 1 over 2 squared. And Q2 over P2 is greater than or equal to 2 over 3 squared. Okay. And if we do the last one, Qx over Px is greater than or equal to x over x plus 1 squared. Fine. So what follows? We can multiply both sides of this equation by Q2 over P2. And you can keep doing that. So I'll skip a few steps, but what am I really going to say? I'm going to say if I look at the product of Q1 up to QX, Q1 up to QX, PX, that's going to be greater than or equal to what? 1/2 squared times 2/3 squared times 3/4 squared up to where? X over x plus 1 squared. Okay. What am I using? I'm using this estimate that they gave us. But notice some cool stuff. 2 squared here cancels the 2 squared here. 3 squared here cancels the 3 squared here. So what is this thing really equal to? 1 squared survives. And what survives on the bottom? It's plus 1 squared. So term by term, each of these guys is greater than 1 over x plus 1 squared. But that means what? The summation of the gamma x's would be greater than or equal to the summation of this stuff. And what does this look like? This looks like the sum. And with 1, it looks like 1/2 squared. Plus 1/3 squared plus 1/4 squared. It's that infinite series. Okay, now you're back in calculus. Does that infinite series converge or diverge? If you say you don't know, fair enough, but look it up. If you look it up, what will you find? This is an example of a p-series, where p is 2. And it's known in general that if you add n to the p, this will converge when what? P is bigger than 1 and diverges when the p is less than or equal to 1. When it equals 1, it's the harmonic series part of it. Okay, so this thing converges from calc. If you ask me why calc, you'd probably do the integral test if you wanted to go further. But anyway, it converges. So this converges. Let's see, are the inequalities going the right way or not? I'm not sure. Maybe I wrote them going the wrong way. So let's go back and look at 20 years. We are in 29. And what do we have these things? Oh, they're not even greater than or equal, they're equal. Okay, so if they're equal, even easier, my bad. And wherever I had greater than or equal, just replace it by equal. Okay, so the sum of this is the sum of that. And this series converges. So every place above here where I had, starting here, I should have just made it equal. That's what they give you there, right? So since the ratio of the Q's over the P's are equal to these, and since if you multiply all those guys together, you just get this. And since that's just the P series where P equals 2, that means this converges, that means this converges, that means what? The birth-death chain is transient. That's what we're trying to show. That's part A. And this inequality should become just equality, right? Does everyone track part A? We're using equation 68, which says if this infinite sum goes off to infinity, then this birth-death chain is recurrent. And if it's finite, then it's transient. In this case, it's In this case, it's transient. What about B? B wants you to figure out the rows. But they tell you how to get the rows, go back to 26. And that would be 26B this time. And there's a formula. So it says use the formula basically in 26B, and then make use of the fact that the sum of the 1 over the squares is pi squared over 6. So you should be able to find the rows from 26B, which is the case where this thing converges. I'll let you play with that one. Okay, so I think we cleared the deck. We've done most of the homework problems except for 26. We'll do that one next time. I better run. Thanks for hanging.
Thank you, Professor.
You're welcome. Hope it helps.
Thank you, Professor. See you Friday.
See you Friday.